What if the most important discovery in the history of interstellar exploration didn't come from the spacecraft everyone talks about? Right now, two machines are drifting through the dark space between stars, and only one of them can still tell us what that darkness is actually made of. Before we go further, do one small thing for me. Tap that like button like you're sealing a message in a bottle and throwing it into space. Because that's basically what this video is. Subscribe if you want more of these stories, and send this to one person who still thinks Voyager 1 is the only spacecraft worth knowing about. Now let's get into it. Everyone knows Voyager 1, it's the famous one, the farthest man-made object in existence. The spacecraft that carries the golden record, humanity's message to any life that might one day find it. The one that crossed into interstellar space in 2012 and never stopped making headlines since. Documentaries love it, textbooks love it. Even people who know almost nothing about space exploration have heard its name. But there is a second spacecraft out there, moving in a different direction, further from the sun in some ways, quieter in every way that matters to the public. Its name is Voyager 2, and for decades it lived in the shadow of its twin. Less famous, less discussed, treated almost like a footnote to a bigger story. Here's the part almost nobody talks about. When Voyager 2 finally crossed into interstellar space, years after Voyager 1 had already done it, it carried something its twin did not. A working instrument. One single functioning piece of hardware that Voyager 1 had lost decades earlier, long before it ever reached the edge of the solar system. And because of that one instrument, Voyager 2 did something Voyager 1 never could. It measured the actual plasma at the boundary of our solar system, directly, with real numbers, real temperatures, and real density readings. It did this instead of using guesses stitched together from other tools. What it found didn't just add to what we already knew, it challenged it. It complicated the story scientists thought they understood. It forced researchers to sit with a very uncomfortable sentence. We don't fully understand why the edge of our solar system behaves the way it does. And now, in the middle of 2026, that same spacecraft is at the center of one of the riskiest engineering decisions NASA has ever attempted. This is on a machine this old, this far away, and this irreplaceable. Let's start from the beginning, because the story only makes sense once you understand how these two machines ended up so different from each other. Voyager 1 and Voyager 2 launched in the same year, 1977, just weeks apart. Voyager 2 actually launched first, on August 20th. Voyager 1 followed about 2 weeks later. The names might suggest Voyager 1 was somehow the leader, the more important one, but that's not what the numbering means. It reflects which spacecraft was expected to reach its destinations first, not which one launched first. Voyager 1 was placed on a faster, more direct path. It would fly past Jupiter, then past Saturn. It used Saturn's gravity to bend its trajectory upward and out of the plane where all the planets orbit. That path gave it a close look at Saturn's giant moon titan, but it came at a cost. Once it curved out of that plane, there was no way to reach Uranus or Neptune. Its road out of the solar system was set, and it was heading for open space faster than anything else humanity had built. Voyager 2 took a longer, more patient route. It also visited Jupiter and Saturn. Instead of angling away afterward, it stayed close to the plane where the planets orbit. That decision allowed it to use each planet's gravity to sling itself toward the next one. Jupiter to Saturn, Saturn to Uranus, Uranus to Neptune. A chain of gravitational handoffs that only works if the outer planets happen to be lined up in just the right way. And in the late 1970s, they were. This kind of alignment happens roughly once every 176 years. Scientists at the time realized that if they didn't launch during that specific window, the opportunity to visit all 4 giant planets would be gone for generations. So they built Voyager 2 to take that longer path. Knowing it would reach interstellar space years after its twin, they also knew it would see things along the way that no other mission would see for a very long time. That decision made Voyager 2 the only spacecraft in human history to visit all 4 outer planets: Jupiter, Saturn, Uranus, and Neptune. Every single one. Nearly 50 years later, no other mission has repeated that. Not one. It remains the only close-up look humanity has ever had of Uranus and Neptune, and it will likely remain the only one for decades more. But that longer path meant Voyager 2 crossed the true edge of the solar system much later than Voyager 1. Voyager 1 crossed into interstellar space in August of 2012. Voyager 2 didn't cross until November 5th, 2018. That's a 6-year gap between the two spacecraft leaving the bubble of our sun's influence and entering the space between stars. For those 6 years, Voyager 1 was our only source of direct information about interstellar space. Every headline, every study, every model of what lies beyond our solar system was built almost entirely on data from one spacecraft. And that data was strange enough on its own to keep scientists busy for years. But it was also incomplete in a way that almost nobody outside the scientific community realized. Here's the piece of this story that gets lost every single time Voyager 1 makes headlines. Long before it ever reached interstellar space, One of its most important instruments had already stopped working. Its plasma science instrument, the tool built specifically to measure the temperature, density, and movement of charged particles, failed back in 1980. That's not a typo. 1980. Before Voyager 1 had even finished its flybys of the outer planets. More than 3 decades before it would ever reach the boundary of our solar system. Think about what that means. The instrument most capable of telling us exactly what the plasma looks like failed. It went silent decades before Voyager 1 got anywhere near the true edge of the solar system. So when Voyager 1 finally crossed into interstellar space in 2012, it crossed blind in the one measurement that mattered most. Scientists had to reconstruct what was happening using other instruments like cosmic ray detectors and magnetic field sensors. They used plasma wave tools that could only pick up indirect signals. It was like trying to describe a room's temperature by listening to how loudly the walls creaked instead of just using a thermometer. Voyager 2 never lost that thermometer. Its plasma science instrument kept working through its flybys of every outer planet. It worked through the long, slow journey toward the edge of the solar system, and through the actual crossing in 2018. For the first time in history, humanity had a spacecraft crossing the boundary with a functioning tool that could directly measure plasma. It could measure on both sides of that boundary at the exact moment of crossing. This is where things get genuinely surprising. In November 2019, 5 separate scientific papers were published together describing what Voyager 2's instruments found at that boundary. And what they found didn't simply confirm the picture built from Voyager 1's data. In several important ways, it contradicted it. The first surprise was about the shape and thickness of the boundary itself. Before this, scientists imagined the edge of the solar system as something relatively thin and sharp. They saw it as a clean line where the outward rush of solar wind ends and interstellar space begins. What Voyager 2 actually detected was a much messier picture. Just outside that boundary, in territory that was supposed to be pure interstellar space, the spacecraft picked up interstellar particles. These particles had pushed inward, mixing with material from our own solar system across space roughly 100 million miles wide. It was not a clean wall. It was a wide, blended transition zone where 2 very different environments overlap. Voyager 1 had seen hints of something similar, but it saw a different signature entirely. It saw a region where the outward solar wind seemed to stall and lose momentum before the true boundary. 2 spacecraft, crossing at different points, years apart, and finding 2 different versions of the same edge. That alone told scientists this boundary is far more complex and far less uniform than any model had assumed. Then there was the location of the boundary itself, and this is where a genuinely strange coincidence appears. Voyager 1 crossed the boundary about 122 astronomical units from the Sun. Voyager 2 crossed it at about 119 astronomical units, almost the same distance. This happened even though the 2 crossings occurred under very different solar conditions. Voyager 1 crossed near a period of high solar activity. Voyager 2 crossed near a period of low solar activity. Scientists expected the size of this protective bubble to expand and shrink depending on how active the Sun was. They thought it would act like a balloon that grows when you blow more air into it. Instead, the boundary sat in the same place. One of the lead scientists on the mission said it plainly. We don't understand why that is. Not a vague guess, not a hedge. A direct statement that our Sun's activity relates to the size of its bubble differently than predicted. The third surprise involved temperature. And this is where Voyager 2's working instrument mattered most. Inside the solar system, the solar wind is extremely hot in the sense that its particles move incredibly fast. Scientists expected a dramatic temperature shift right at the boundary as hot material met colder plasma of interstellar space. Voyager 2 confirmed that shift was real, and even sharper than predicted. But the bigger discovery was on the other side. For the first time ever, a spacecraft directly measured the temperature of the plasma in interstellar space itself. The number came out to somewhere between 30,000 and 50,000 degrees Kelvin. Hot by ordinary standards, but dramatically cooler than the tens of millions of degrees measured just inside the boundary. Scientists had estimated that number before, using theory and modeling. The actual measurement was off by a factor of 2. An entire generation of assumptions about interstellar temperature was corrected in a single crossing because one instrument still worked. Think about how quietly that correction happened. No press conference dramatizing it, no viral headline calling it a paradigm shift, just a spacecraft passing through a boundary once, taking a reading nobody had ever been able to take before. It was rewriting a number that had sat unchallenged in textbooks and models for decades. That's how most real scientific progress actually happens. Not with dramatic announcements, but with a single working instrument. In exactly the right place, at exactly the right time, it quietly corrected something everyone assumed was already settled. And then came what one of the mission's senior scientists called the most remarkable finding of all: the boundary leaks. Not occasionally, not as some rare exception. as a basic feature of how it works. Material crosses in both directions all the time. On Voyager 1's approach, scientists detected tendrils of interstellar particles pushing inward, slipping into the edge from outside. On Voyager 2's approach, years later and from a different direction, they detected something almost like a mirror image. Low-energy particles from inside the solar system were leaking outward into interstellar space before the spacecraft had even crossed. Two different spacecraft, two different directions, and two different mechanisms showed the same underlying truth. This boundary is not a wall. It behaves more like a coastline where waves and currents move constantly in both directions. It blurs exactly where one ocean ends and the other begins. One of Voyager's longtime project scientists described it in a way that stuck with researchers for years afterward. He said, "The Voyager probes are showing us how our sun interacts with the material that fills space in our galaxy." Notice the wording. Not where the sun's influence ends, but how it interacts. That is a completely different picture. It is not a clean separation between our solar system and everything beyond it. The real picture is messier and more dynamic. Even now, both spacecraft are still traveling through what scientists call a disturbed transitional region. Even at 13 and 15 billion miles from the sun, they still haven't reached truly undisturbed interstellar space. Our sun's fingerprints are still detectable in the particles surrounding these two machines, even this far out. Take a second and sit with that. We built two machines nearly 50 years ago with very weak computing power. And they are still teaching us that we don't fully understand the edge of our own solar system. If this is blowing your mind, hit that subscribe button like you're locking in a front row seat to a story unfolding. This channel exists to explain real science the way it deserves to be explained, without exaggeration or noise. If that sounds like your kind of channel, this is a good moment to join. Now here is where the story becomes unexpected. The discoveries at the boundary are only half of what makes this moment so important. Think about why two spacecraft existed. In the 1970s, mission planners made a deliberate choice. They didn't send one spacecraft and hope for the best. They sent two on different paths, aimed at crossing the boundary from different angles and under different solar conditions. That wasn't luck. That was design. A single spacecraft can only tell you what it found in one place at one moment. It can never tell you whether what it found is typical or a strange exception. Two spacecraft build a real picture. What the planners could not have predicted was that the most important instrument would fail on one and survive on the other. That was chance, and engineering luck, and maybe a little bit of stubborn hardware refusing to quit. Voyager 2's plasma instrument kept functioning for over 4 decades in one of the harshest radiation environments in the solar system. In doing so, it filled a gap that had existed in our data since 1980. That is the real story hiding underneath. A mission built on careful planning ended up depending on something nobody could have guaranteed in advance. And now, in 2026, that same aging spacecraft is facing its biggest test yet. It is not from radiation, but from power. Both Voyager spacecraft run on radioisotope thermoelectric generators, converting heat from decaying plutonium into electricity. At launch, each spacecraft had about 470 watts of power available. This was enough to run 10 science instruments. But radioactive decay doesn't stop. Every single year, each spacecraft loses about 4 watts of available power permanently. Engineers have spent decades managing that decline, like managing a candle burning down in a house with no replacements. One by one, instruments have been shut off because keeping them running was no longer worth the power it cost. Of the 10 original science instruments, most have already been switched off. On Voyager 1, only 2 remain active today. On Voyager 2, 3 instruments are still running, including that same plasma-related equipment from the historic 2018 measurements. In April of 2026, engineers made the difficult decision to shut down one of Voyager 1's remaining instruments. It had been measuring low-energy charged particles almost continuously since the mission began. Nearly 49 years of operation. It was switched off because keeping it alive was starting to threaten the survival of the entire spacecraft. It was a hard call, but it wasn't the end of the plan. It was a bridge to something bigger. That bigger plan is nicknamed the Big Bang, and it might be the riskiest thing NASA has ever attempted so far away. The idea is to completely reorganize how power flows through the spacecraft all at once, rather than one at a time. They will swap a group of devices simultaneously. They will turn off systems and turn on lower power alternatives. This coordinated move is not gradual. The reason for doing it this way is to avoid the danger of instability. There's a moment where the spacecraft sits between its old setup and its new one, neither fully here nor there. That in-between moment is dangerous because of built-in fault protection systems. These safety routines might shut things down incorrectly. If engineers make changes slowly, they risk lingering in that unstable state too long, giving systems more chances to panic. So the plan is to move through that danger zone as fast as possible by making every change at once. All or nothing. Now remember the distance. A command sent to Voyager 2 takes many hours to arrive, and the response takes just as long. Every single check and diagnostic step costs more than a full day of waiting for one round trip of information. There is no way to watch this happen in real time and hit pause if something looks wrong. By the time they see it, it is hours old. Any correction they sent would take just as long to arrive. It's like sending someone into a maze blindfolded. Engineers chose to test this on Voyager 2 first because it has a slightly larger power cushion and sits closer to Earth. Tests began in the spring of 2026, with the far riskier attempt on Voyager 1 planned for no earlier than July. If everything goes well, there's even hope that the instrument shut down back in April could eventually be switched back on. Sit with what's actually happening. A machine from the 1970s is about to undergo a coordinated overhaul of its power system. This is executed across a communication gap of more than a day, with no ability to intervene in real time. If it works, it could add years to the operational life of humanity's only connection to interstellar space. If it doesn't, there's no backup plan. This is the kind of moment history usually only recognizes after the fact. Right now, it barely makes a ripple outside the small community paying close attention. Think about how strange that is. If a rocket exploded on a launch pad, it would dominate every feed. But this risky power reconfiguration barely registers. Humanity's only working plasma instrument hangs in the balance. This gap in attention might be the strangest part. There's another detail. The engineers aren't guessing. They know exactly how much power remains because plutonium decay is predictable. Everything else, like antennas and wiring, carries uncertainty. But the power loss of 4 watts a year is certain. The whole Big Bang procedure exists because a team decided to fight for every extra year they could pull out of it. The findings from Voyager 2's crossing didn't just satisfy curiosity. They exposed real gaps in our understanding. Why does the boundary sit at the same distance regardless of solar activity? Nobody has a solid answer yet. What causes particles to leak in both directions? Still unknown. What is the true overall shape of the protective bubble? Some models suggest a long tail like a comet, others a sphere or a squashed fruit. 2 spacecraft are the only tools to test this. The magnetic field readings matter too. Voyager 2's magnetometer keeps contributing new data to map the galaxy's magnetic structure. And underneath sits a heavy truth. There is no replacement coming. No second mission is currently traveling there. When these two go silent, the flow of information stops completely. Every unanswered question will sit unresolved for generations. That's why every extra year matters. The Big Bang is an attempt to buy more time with a part of the universe we cannot reach. There have been early conversations about a future interstellar probe designed specifically for measuring the interstellar medium. But conversations are not funding or a launch date. A purpose-built mission would take decades to reach Voyager 2's current position. There is no version of the near future where humanity has a second set of eyes out there. These aging machines are it. Share this video with someone who thinks exploration ended with Apollo. Let them see the frontier is 13 billion miles away. Let's appreciate what Voyager 2 accomplished. It remains the only spacecraft in history to fly past Uranus. It discovered 10 moons and 2 rings. It measured Uranus's bizarre tilt in a magnetic field that is strangely offset. It remains the only spacecraft to fly past Neptune. It measured supersonic winds faster than anything recorded on other planets. It captured images of Neptune's moon Triton, revealing active geysers shooting material miles into a thin atmosphere. It discovered moons at Jupiter, captured details of Saturn's rings, and confirmed volcanic eruptions on the moon Io. It returned images of Europa showing fractured surfaces that first hinted at a hidden ocean beneath the ice. All of that came from technology built before personal computers and the internet existed. It is still transmitting 49 years later. A small team in California is keeping that legacy alive. They had to learn programming languages from an era before their careers began. This knowledge is passed down personally because no modern manual can fully replace it if it's ever lost. They are sending commands across billions of miles, knowing a single misstep could end contact permanently. Somewhere, there are people whose job is to keep a conversation going with a machine that left home before they were born. The results from these power tests are coming. You're going to want to understand what you're looking at when the headlines arrive. NASA could have let both spacecraft coast towards silence years ago. Instead, a team keeps choosing to fight for a few more months. Comment the word signal below if you want a follow-up video on whether the Big Bang worked. It helps the video reach others. Voyager 1 will always be the name most people remember. It carries the golden record and was the first to leave the solar bubble. But Voyager 2 filled in the picture. It's the only one to visit 4 giant planets and give direct measurements of the interstellar space. It revealed a boundary that is far messier and less understood than anyone expected. It is now at the center of a bold decision. If it works, we get more years. If it doesn't, we lose a connection that took nearly 50 years to build and cannot be replaced. Out past the edge, 2 small machines are still moving, listening and measuring. They send back whispers across billions of miles. Voyager 1, US opened the door. Voyager 2 is still standing in that doorway describing what is actually inside the room. 50 years from now, these machines will still be out there in the dark, carrying a golden record nobody may ever hear. But there will always be this moment in 2026 when a team risked everything to buy more time for a machine that gave so much. We didn't build these to last forever. They outlived almost everyone who built them and are still answering questions today. The signal is still coming. 16 hours at a time, across 13 billion miles of silence, it is still coming. And for as long as it keeps arriving, there is still more of this story left to tell.